Okay, shall we start? Okay, so today we're going to talk about um, early quantum error correction code, not the current one. So, this quantum error correction codes are for. Uh, well, it's not that I'm not saying that it's not practical, but it's small. It's a very small sort of error correction code. So practically, it's not used, but it's has the essence of how the error correction works. So we'll discuss that here. Um, so let me think about what is so now before we talk about error correction code, what is it? So quantum error correction code. So first, it has to be used to correct errors. So it somehow detect error, quantum error. So as I said, there are two types of quantum errors, an X error and an Z errors. So it has to be able to detect these errors. But then the second is more important. We don't want to change the state, right? Even if we know that there was an X or Z errors occurred, if we try to measure it, if we measure it, then the state is collapsed. It's ruined. So we don't want to. We want our quantum state to be intact. So preserve quantum state. So let's think about this way. So so in order to keep these two principles in our quantum error correction code, we need to change our mindset from physical qubit to logical qubit. So the logical qubit is a collection of physical qubits that acts like a qubit. So as long as this collection act as a single qubit, act as a something that conveys the same information as the physical qubit conveys, then we can consider it as a qubit, but it's not real physical qubit, so we call it logical qubit. So think about this way. So if I just take 3 qubits, let's say x of size 3, okay, and I want to just simply store the information of 0 qubit. So if this is 0 0 0, or then we call it logical 0. And if it's 1 1 1, and we call it logical 1. So let me say it this way. So logical 0 and logical 1, meaning that it's 0 qubit and 1 qubit. Okay. So what's the problem here? The problem is, what if we have, say, 0 0 1, or 0 1 0, or 1 0 0? So in this case, what classical error correction does is count the number of zeros, and if it's bigger than number of 1, then you consider it as 0. That's the easiest way and naive way of error correction. You take the larger number of qubits to make it kind of correct. But the problem is, well, if you simply take the measurement, everything is ruined, right? So let's say if I have the quantum state encoded in the logical qubit as a plus state, which means that I have 0, 0, 0 plus 1, 1, 1, meaning that it's logical plus. How do we detect whether this has an error or not? That's a problem. If there is an error without collapsing the state. So, for example, our code, our state could have something like this. Let's say it's 1, 0, 0 plus 1, 1, 0. Okay. I want this state to be considered as same as the plus bar state, a logical plus state, still, but also I want to detect an error for the future purpose, so that I can consider that in a future circuit. So anyway, if this happens, what happens is I could take a measurement. So, well, if my quantum state was in the ideal plus state, then all the measurement is all zero or all one. But if I take a measurement and I see one of these in a quantum state which has occurred error, then I get 100, 110, either one of these, then I don't know what to say. I don't know what to say, whether there was error occurred, or maybe probably error occurred, which part was an error, and or how to how to um, correct those errors. So that's the problem. So let's think about this way. I'll just give you the example of the error correction code, and then let's think about this together. 5-qubit code is defined as follows. So I'm going to define a gate, 5 gates, M1 to M4, in the following way. So M0 is, so since there are 5 qubits, 5 physical qubits, there are 5 gates applied to each qubit. So starting from the rightmost gate, it's a qubit 0 gate, to the leftmost gate, it's a qubit 4 gate. So first one is set XX, set I, reading from the right to left. And the second one is this. And the third one is this. And this. And this. So this is not fixed. So you can see what's the rule of there are only 3 types of gate, I, Z, and X. And you can see that if you take one qubit, one specific qubit, let's say I pick middle one here, then you can see that there are 2 X and 2 Z and 1 I. Okay. So as long as you keep this rule for every 5 qubit, then you can say it's a 5-qubit code. So what does it do? So what I do is I take the logical 0 to be this. So I say M0 up to M3. So here the thing is, if you combine all these 5 gates, if you apply all the 5 gates M0 to M4, it's an identity gate because there are always the even number of X and even number of Z. It cancels out. So you don't apply all the M0 to M3, M4. You only have M0 to M3. 2, 0, 0, 0, 0, 0. And that's my logical 0. And this is my logical 1. So what are we doing here? So it's complicated to compute all this, but think about one operations. So let's take 1 square root of 1 plus m0. Okay. So if I apply that to 0, 0, 0, 0, 0, what happens? So m0, maybe. So m0 is iz, xxz. So only applies to xx applies to second and third, right? So it becomes over square root of 2. So 0, 0, 0, 0, 0 plus what? 0, 0, 1, 1, 0. Right? So you take, so that's the right and leftmost gate. So that's the last thing you have to apply. But I'm just showing you what's happening here. And so actually you can change the order of the multiplication. So look at the mi's here. So if you look at the m1s and m0 and m1, what happens is you have zx and xz on the first qubit and third qubit, right? The rest of the qubits either have one z on it or two x's. So you have two qubit places where you have one x and one z. So when you multiply m0, m1, then you're applying xz and zx onto the first and third qubit. Now, if you suppose that you reverse the order of multiplication, suppose that you apply the m0 first and then m1 next, what will happen? So you change the order of z and x operator on the qubit 1 and qubit 3. So if you apply xz or zx on one qubit, and if you interchange the order of action of gate, then you get the minus outside. You get the minus coming out. But there are two places of the qubit among the 5 qubit that you reverse the order of order of action of x and z. So there are two minus come out. So basically, these m0, m1, you can change the order to get the same result. Okay. The same thing for these m gates here. So these are the same. I can just erase everything here. So I, mj is same as mj, mi. So in this case, you can interchange the order of action of these gates, whichever order you want. So these are all commutable. Okay, so you can actually apply 1 plus m0 first, and then apply the rest of the parts next. Well, okay, so let's try to do it together. So what will happen when I do this? So first, I get this one, and then if I apply 1/2, 1 plus m1 onto let's see, here, what happens? So M1, let's look at the M1 here. M1 has two z's. So basically, z doesn't change 0 or 1, only changes the sign of one ket, but there are two z, so even if it changes the sign, so you have to take consideration of changing the sign, and also two x's on there. So it's going to be 1/2 of, so 0, 0, 0, 0, 0 plus 0, 0, 0, 1, 1, and plus, now that's after applying M1 here. Oh, so sorry. That's, yes, that's after applying here. But I think I should write this one after applying the identity gate first. So let me write this first. So 0, 0, 0, 0, 0 plus 0, 0, 1, 1, 0. That's after applying the identity gate on there. Then plus, so let's apply M1. So if you apply M1 here, it becomes 0, 0, 0, 1, 1. And on here, so you have Z on here and X on here. Okay, so 0, 0, 1, 0, 1. Okay, but now you have a minus because you have 1 where you apply Z. So that's after applying 1 plus M1. And let's do it again. So after M2, you apply this thing. So getting complicated, but every time you get doubling the number of summation inside of the superposition, the base state, and then you also have this coefficient 1/square root of 2, so the strengths of the quantum state are remain the same as 1, but still it's getting superposition of lot more and more quantum states. So if I finish this part, so M2, going back to the definition here, remember that xz(i)zx, that's M2. So when I apply this, the same thing remains, and the next one is 1, 0, 0, 0, 1 plus 1, 0, 1, 1, 1. But now we have a minus because here the second qubit is applied by z here, and then plus 1, 0, 0, 1, and 0, get minus here, and then you get 1, 0, 1, 0, 0, minus. So you get a base state applied, summed up to a superposed state after applying this gate. So I don't want to do it anymore because what we are doing here, it is actually getting an eigenstate. We are trying to get an eigenstate. What does that mean, the eigenstate? So let's say, what happens when I apply M0 after I apply 1, 0 onto any state, psi. So let's say it's a 5-qubit state. Psi is a 5-qubit state. So after I apply this gate, I apply M0 gate again. Okay, so let's compute this. So I can do the computation, the first part of the gate computation first, and then apply to the 5-qubit gate, right? So that's the same thing. So when I do this, then I get M0 plus M0 square. Right? So what is M0 square? What will be the M0 square? Because M0 is always consists of X and Z gate applied to each qubit. When you do it twice, you get to the original state. So it's same thing as identity gate. Right? So this becomes 1 plus M0. Okay. So what does it tell you? So it tells you if you take the entire these states as something, let's say, let me call this as phi. Okay, so call it phi here. Then it means that m0 times phi5 equals to phi5, right? So what do you call that kind of situation? So M0 is simply a matrix and B0 is a vector. And when you apply the matrix to a vector to get the some scalar multiple of the same vector, it's the eigenvector. So we call this eigenstate. So V5. So how did we get the V5? By applying this. Is a eigenspace, eigenstate. Let me write it clearly here. Eigenstate of what? M0. Okay. So going back to our definition of logical zero and logical one of our state, the what we are doing here is making an eigenstate of m0 to m3 by multiplying these gates. By multiplying these gates, we are making this zero base state into an eigenstate of m0, m1, m2, m3, up to m3. So 0 is the okay, so the eigenstate of m0, m1, m2, m3 with eigenvalue plus 1. So that's the important thing. So we made eigenstate and we call these eigenstate as a logical zero. So what about 1? So what happens to 1? So 1 is the eigenstate with eigenvalue minus 1. So why is that? Well, actually, let's see. There are many ways you can prove this. Yeah, well, let's. I don't think it's hard to think about this, but anyway, so look at the definition again. So we have these. What happens here is we apply the same state, the same gate here to the state where we apply 5 exit gates on 0 states, right? So when when I say it's eigenstate with eigenvalue of 0, I want to say if I apply mi for any I from 0 to 3, it gives me minus I, the logical I. So let's find out why that is. So m0, 1 over 4 over 2, 1 over 4, sorry, 1 plus m0 up to 1 plus m3 and 1, 1, 1, 1, 1 here. Um, right? So is it? No, no, no. So um, oh, sorry. So it's not one. So actually, it's not right. So um, okay. So that's I should change this a little bit. Oh no, that's right. Yeah, that's right. Sorry, sorry. So I think this is not right. This is not the right thing. Sorry. That's not what I want to claim. Okay, so 0 is eigenstate. And also 1 is the eigenstate. That's what I want to say. So, and 1 is also eigenstate, right? So what I want is for every mi, if I apply that to the logical 1, I want it to be 1. And let's try to find out why that is. So it's 1 over 4, 1 plus m0, and 1 plus m3 apply to 1, 1, 1, 1, 1, right? So as I said, mi, mj always commutes. And if you combine mi with 1 plus mi, then it's the same thing. So it's the same thing, 1 over 4, 1 plus m0 dot 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 to 1 plus m3 apply to 1 1 1 1 1 here. So because they are the same thing. So we can say that this is equals to I mi and this is equals to I. So I is also the eigenstate of mi here. And there are more things to talk about. So what is the mi square? When you, as I said, it's 1, right? So in the linear algebra, if you remember it. So when you have a matrix whose square is 1, there is always an eigenvalue or eigenvector for eigenvalue plus 1 and minus 1. So these are the eigenvalues corresponds to plus 1, 0, and 1. And there are also the eigenvalue corresponds to minus 1. Okay. Yeah, well, that's not really relevant here. So anyway, so how do you get, how do you change your logical 0 to logical 1? If you apply the x gate on every 5 qubit state, like every 5 qubits in your logical qubit, then you get 1, right? So think about this way. So we have 5 x's and apply to 1 over 4, 1 plus m0 up to 1 plus m3. And then there's a 0 here of 5 qubit. Okay. So why is that? So I want to interchange the order of my five x gates with the rest of the gates. So let's do it one by one. So if I take 5 qubits here and 1 plus m0, then I want to interchange the order of multiplication like this. So when I apply to 1, the identity gate, that's the same thing I identity gate here. But when I apply to m0, what happens? When 5x's multiplied with m0, it's x, 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 times, what is it? I, Z, X, X, Z, right? So it's same as X on the 5th qubit, XZ on the 3rd qubit, X squared, so it's I on the 2nd qubit, and another X square on the 1st qubit, and then XZ on the 0th qubit, right? But then if you take the opposite order of the gate, then it's I, Z, X, X, Z times X, 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 X. So X fourth, X on the 4th qubit, ZX on the 3rd qubit, and X squared on the 2nd qubit, and X squared on the 1st qubit, and ZX on the 0th qubit. So this one is XZ. The only difference between the two operations is on the 0th qubit right here and the 3rd qubit. So what are the difference? They change the order of multiplication of X and Z. You have a minus sign appears on one of these in order to change it back to the order of the other thing. But then you have the same thing on the same two places, so you have two minus coming out. So you get same thing as X fifths, 5X gates on M0. So you can change the order of these operation to any of these operations. So you can move it to all the way back to here. X gates can be moved to all the way back to here so that it can apply directly to 0. Okay? So therefore, it's 1, logical 1. Okay? So now we have a logical 0, the concept of a qubit 0 and qubit 1, and you have X operation. How about Z operation? Okay. How about Z operation? We simply take, let's see, Z5 to 0. What will happen? Well, not 0 here, maybe 1. Well, let's do the same as a 0 here. So you can imagine that same thing happens in the Z case. So if you have a 5 Z gate as a 1 operator and then apply to all these things again, and there are two places, every MI has two X gates. So if you change the order, you have 2 minus comes out. So you can always interchange the order. But this is same thing as 1. Sorry. This is the same thing as applying all this M0 up to M3, and then Z follows to 0, 0, 0, 0, 0, right? So when you apply Z to the 0 ket, nothing happens. So therefore, it's 0. How about 1, logical 1? What will it be? The same thing, that can be go all the way down to just before you apply it to 1. So 1 over 4, 1 plus M0, 1 plus M3, and Z5, 1, 1, 1, 1, 1. What happens next? What's the result here? How many ones here? 5. Okay, so you have 5 minuses. That means minus, right? So it's minus 1. So when you have Z gate on every qubit, you can change, you can consider that as a logical Z gate of this logical qubit. So here, so 0, 1 are the base logical qubit, and now I'm going to denote x bar as x 5 times x on every qubit, and z bar are the logical x and z gate. So of course, a qubit can have lots of other gates like Hadamard gate and other, but this one at least have x and gate z gate. It's a logical gate, so we can consider this logical qubit as if it's just one physical qubit which has x and z gate applied, right? So that's good because well, we made a new concept of qubit. Now, why we are doing this? Because we also want another additional thing going on because so that we can correct an error, correct a physical error. How do you detect an error here? So let's think about what happens when we have error occurred in one of the qubits. So if X error occurred on qubit 0, then, well, the initial state was, let's say, 0 logical qubit. Then what happens here? It becomes something, so let's see, x0 is occurred on the logical qubit x0. So in order to see what actually happened here, let me write down this in a longer form. So it's 1 over 4, 1 plus m0, 1 plus m3 times 0, 0, 0, 0, 0. So to distinguish that this is not a gate applied to that this is not a gate, this is an error. To indicate it's an error, I'm going to put the tilde on top of x0 here. Okay, so x0 occurred. I'm not going to use all the superposition long form of the x0 bar. Instead, take this x error as if it's a gate, because that's how we conceptualize the error, as if it's just unwanted gate applied to certain qubit. I'm going to move this around all the way down to here and see what happens along the way. So let's see what happens when I switch the order of x0 and m0. Of course, it's x0 and x0, m0. And I know that m0 is I set x set here, right? So, so these 4 qubits are not affected by the error occurred at the qubit 0. So this only goes to the qubit 0 Z gate here. Therefore, this is x0 plus I Z x and x set at the 0th qubit, right? So what happens when I interchange the order of the gate? I get minus x0 bar minus izxx set x tilde at the 0th qubit. Therefore, I can write it as 1 minus what? m0 times x tilde at the 0th qubit. Okay, so when I change when I try to move my x0 to the right side of my operator, I change the sign inside the parenthesis, right? So what will happen at the m0, m1? So now I'm having m1 here. So m1, as I write here, is zi zxx. What will happen if I put x0 tilde to the right? Does sign change or not? Does it changes the sign? Because it applies to here, the x gate, right? You have two x gates. You can change the order of two x gates, of course. So the sign doesn't change. But just simply doing the math, just simply doing algebra here. So 1 plus, it's m1 times x0 tilde. Okay? So sign doesn't change. How about m2? So here, x0, 1 plus m2 is x0, 1 plus x z I z x. The sign changes? No, because still you have x on the zeros qubit. So it's same as 1 plus m2 x0. And how about m3? So what is it? 1 plus zxx zi. Well, it's a I. But there's one z. I'm sorry, so I was looking at the different thing. So we have x, x, z, I, z. Okay, so now it changes the sign again. Okay, minus m3 times x0. Okay, so going back to our situation here. So what is this? Suppose there is an error occurred at the zeros qubit on the logical 0. It is same as 1 minus m0, 1 plus m1, 1 plus m2, and 1 minus m3, and x0 here. Okay, that's what it happens. Okay, so what I'm gonna do is I'm gonna do the same thing for all other qubits, qubit 1 to qubit 4. So let's make a table. Okay, so here m0, m1, m2, m3, and let's say x0, x1, x2, x3, x4. So there are 5 qubits. So all the possible error that could occur on each qubit is x0 to x4, and there could have a z error on each qubit also. So let's take another qubit here. Z0, Z1, Z2, Z3, and Z4. So when I change all these, let's see, take this x0 all the way up to here, I count how many minus occurred. Okay? I will count how many minuses occurred. So here, when x0 is moved up to all the way to the right, m0 changed the sign, m1 didn't change the sign, m2 didn't change the sign, m3 didn't change the sign. And let me take another one, so maybe it'd be convenient to have this. So what if I had x0 applied to m0, m1 plus m4? So here, let's see. I'm going to take another row here, even though it's not in the construction of the logical 0. xx set I here. So then it's the same thing because we have I here. So 1 plus m4 x0 dot, right, tilde here. So m4 doesn't change the sign. So I want to fill up all the signs of this, fill the tables, all the parts in the table with the plus or minus sign, depending on whether the sign changes. So let's try this. Okay. So start from x1. Try x1 here. So do we all have the same table? So I'm gonna write m0 to m4. I'm gonna copy paste the definition here again, so that we don't confused. And here, this is our table. So according to this table, let's figure out which part is plus and which part is minus. So basically, you just count where, so just locate where x and z's are, right? So when you look at the table for xi, then you see where z's are in the ith qubit of m0 to m4. So, and x1 means that you just take the ith first qubit, qubit 1 here, and you can see that there are Z here and Z here. So only those cases, when you interchange the order, get the minus sign. So you get 2 and 4 minus here. Yes, and everything rest of the part is plus. Now, we can do this for how many? 10. And actually, if there's no error occurred, then everything is positive, which means no minuses. Okay. So why are we doing this? So think about this. Um, when I have okay, so when I have any quantum state, 5-qubit quantum state psi, and I applied 1 minus mi, not 1 plus mi, then what is this state? Let's apply mi onto this quantum state. Then this is same as just multiplying mi inside here. I get mi minus mi squared psi 5. So this is equals to minus 1 over square root of 2, 1 minus mi, right? So if I take this entire thing as some sort of psi state, this is phi state, sorry, phi state here, then it means that phi is eigenstate, but its eigenvalue is minus 1. Okay? So look at going back to our situation. So we assume that, for example, there was X error occurred and at the ith qubit on logical 0. So it changed the state into this. So when I move xi all the way to the right side of this, it becomes what? 4 here, 1 minus, sorry, Oh, I have to specify one thing here. So let's say x0. Okay, so again, so I have 0, 3. So 1 minus m0 plus m1, 1 plus m2, and 1 minus m3 x tilde 0, 0, 0, 0, 0. So, okay. Um, all right. So think about entire state here. The entire state is going to be called, let's say, psi state. Okay? So what's the? I'm going to try. I'm trying to think about this psi state as an eigenstate of Mi. So let's try to multiply m0 to phi state. So as I said, the phi m0 is multiplied on 1 over 4, 1 minus m0, blah, 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 whatever, it doesn't matter. And this same thing as 1 over 4 minus 1 minus m0, blah, 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 because the same calculation, because m0, 1 minus m0 squared is minus to the 1 minus m0. So since I define this whole thing as a phi here, this simply, the difference is minus. So it's minus of phi 5. Okay. So what is phi 5? So phi 5 is the state of the logical zero when the x error occurred on the zeros qubit. So it means when the x error occurred at qubit 0, it becomes an eigenstate of eigenstate of m0 with eigenvalue minus 1. So it changes eigenstate with m0. So how about m1? If I have m1 applied to phi 5, now the situation is different. So m1, 1 over 4, 1 minus m0, 1 plus m1, so on. Now, I can move around m1 with a different index mi, so it can move to here. So when I'm at the middle of 1 minus m0 and 1 plus m1, then I can safely also move m1 to the right-hand side of 1 plus m1 without changing any sign, or without putting any sign here. And then well, actually, it's vanishing here, right? M0 multiplied to 1 plus M1, it's same thing as 1 plus M1. Right? So it's same thing as phi, original phi. So phi is still the eigenvalue with eigenstate with eigenvalue plus 1 as before. So remember that phi is the state after we assume that x error occurred at 0. M1, as an eigenstate of M1, it doesn't change its eigenvalue, but it changes the eigenvalue for the as an eigenstate of M1. So what this table says is that whether the quantum state, is changing to a different eigenvector with a different eigenvalue. So it changes the eigenvector on m0 and m3 in this case. So what if x1 is occurred? What if x error occurred at the qubit 1? Then after the occurrence of this error, the quantum state becomes an eigenstate of M2 and M4 with eigenvalue -1 for these two cases. And rest of the cases, it is still eigenstate. So whether or not error occurred or not, always the states are eigenstates. It's matter of what is the eigenvalue. It changes the eigenvalue. So I want to see what for which gate mi does the eigenstate has been changed its eigenvalue. So that's my question. So x and z error preserves eigenstate of 0, logical 0, logical 1, but it changes the eigenvalue of some mi. So we need to detect which mi, or maybe, okay, so we need to detect the eigenvalue of the current state for every mi, for I from 0 to 4. So I want to find out the eigenvalue. Okay, so that's all. So how do we find out the eigenvalue? So let's think about this way. So I have 5 qubit code and another 5 qubit code, 5 qubit, and I'm going to apply Hadamard on the top register, and on the bottom register, I'm going to have a target. I'm going to consider it as a target qubit for mi. Okay. And then I'm going to measure the top register here. Okay. Oh, so sorry, so it's not 5 qubits, so it's just 1 qubit here. All right. Well, it doesn't really matter, but let's see. It doesn't have to be 0, so let me put it phi. So phi is supposed to be the eigenstate. So it's an eigenstate of mi. So simply, we don't know its eigenvalue. So let's compute the step by step and then see what we get. So let's say our conclusion, the read-off of the measurement is C. So first, let's skip the 0 stage. And at the first stage, let's say phi2, phi1, here is phi5 tensor plus state. Right? And what is the phi 2? After this stage, I apply controlled mi. So controlled mi means that depending on the control qubit, the first register, I decide whether I apply mi to the 5 qubit register here. So since mi is simply the separate operation on each qubit, it's a collection of controlled x and controlled z. Okay. So let's see if the control qubit is 0, I don't have nothing. I don't apply anything. 1, then I apply mi to psi 5. Right? That's what happens. So, and then at the third stage after this, I apply Hadamard again. So it becomes, let's see, 1 over square root of 2 v5 tensor plus mi v5 tensor minus. So let's collect about the two. So let's collect the case when we have v5 plus mi v5, where the control qubit is 0, and square root of 2 v5 minus mi v5 1. Okay. I can separate into these two. Now we can see something similar to what we saw before. So the first state in the superposition is 1 over square root of 2, 1 plus mi applied to v5 tensor 0. And the second is 1 over square root of 2, 1 plus mi applied to v5 with tensor with 1, right? Now, after this, we take the measurement. So we either detect this one or detect this one. So what happens when C turns out to be 0? It says that our state is this. So when C is 0, sorry, it's a minus here. Okay, yeah, let's go backward. So let's try. Actually, this is a forward. So we deduce the quantum state from the measurement, but what happens is actually we have the quantum state which leads to our measurement outcome. So let's suppose that V5 is plus one eigenstate. So if this is the case, then what happens is we have no this case. So 1 minus mi psi is actually 0, right? So in this case, we have 1 minus mi applied to v5 is equal to v5 minus v5, so it's 0. So we don't have the second superposition, right? So this whole stage, the psi 3 stage, is simply 1 over square root of 2, 1 plus mi. So actually there's no 1 over square root of 2 anyway. Anyway, it's psi 5 tensor 0 here. And then, yeah, so it's a 1 over 2 actually. No, 1 over square root of 2. Yeah, this is the stage. And since we have assumed that this is true, but this is same as psi 5 tensor 0. I think that's 1 over 2. I think I forgot to put 1 over square root of 2 at some point. So here, what did I forget? Is that right? Where did I forget the square root of 2? Where? Can you say it louder? Plus 3? Psi 3? Yes. Psi 3. Where? Where is it? Ah, wait. I think it's lagging. So the psi 3. Oh, wait. If psi 3, which part did I missed? Oh, I think I. Oh, okay. So there is a 1 over square root of 2 here. So this. So this whole thing is 1 over 2. So 이게 좀 느리네요. So anyway, so now it's 1 over 2, and it becomes simply psi 5 tensor 0. So when phi is eigenstate of mi, then what we detect after the measurement is 0. Okay? So when you read up 0, then we can assume that this state, our current state, is plus 1 eigenstate. Okay, eigenstate with plus 1 eigenvalue. What if it's opposite? What if it's minus 1 eigenstate? Then 1 plus mi v0 is now 0. So this part vanishes. Only this part survives. So we have psi 3 equals 2. These are all 1 over 2. 1 minus mi v5 tensor 1. And what happens to this multiplication this here? It's the same thing as v5 tensor 1. So in this case, we only see 1 in the readout of the upper register. So by taking the measurement on the first register, you can say whether our quantum state stored in the lower 5 qubit register is either plus 1 eigenstate or minus 1. Okay, so as I said, if you have an error, then it changes the plus and minus eigenvalue of the eigenstate. You take the measurement of this mi for I equals to 0 to 4. So you take the 5 control gate, and then you read off the result. And what you get is, if there is no error, everything is positive, everything read off as 0. But if there's an error, then you will see 2 ones on 2 ones here, some places, like here, according to the table. So for example, if you had x0, you will see 2 minuses on the first. Then, if you see these two measurement outputs 1, then you can use that, okay, so there is an error on the qubit 0. That's how we detect an error. Okay? So, in fact, the circuit looks like this. So you have 5 qubit. So this is data qubit. And then here is another 5. It's called here ancilla qubit. So it's called a syndrome measurement. Without changing the data qubit, without changing anything on the data qubit, you simply detect whether there is an error or not. So you're not really, it's not that really you don't change anything. You don't change the eigenstate. You don't change the fact that the data qubit has some eigenstate of the mi gate. You don't change that fact. Still, you can detect whether it's a plus eigenstate or minus 1 eigenstate. So for each ancilla qubit, you apply, so here's M0, and here you took the M1 here, and so on, up to the last part, M4 here. So and then you take the measurement for all these 5 ancilla qubit. So to get 0 or 1. So if you have a 1, then it means that there is an error. So you have to go to the table and then find out which error it is. So the one thing before I finish is that, okay, so it can detect one error. Only detects one error, one X or one Z. Okay? What if 2 errors occurred? So, for example, you could have, let's say, minus, plus, minus, 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 like this. After you take the measurement on this circuit with the ancilla qubits, get this one. Okay, but the combination of having these could be having x0 and x1, but there could be another combination. For example, you could have a minus minus here and minus minus there. So you cannot tell which one is actual error. So this code can only detect one error among X or Z errors, not independently. Combining all the errors, including X and Z, it can only detect one error at one qubit location. Okay. But now, you see the idea here. If you have more physical qubit and more, not the same way you designed here, but you have a different way of designing, then you may be able to detect X and Z error independently, or you can detect more errors, more than one errors, using the similar ideas. The idea is that your state, your logical qubit, the logical qubit information stored in the multi-physical qubit is always an eigenstate of your measurement, MI, like this one's. Okay, so you don't change the fact that it's being the eigenstate. You only changes what's the eigenvalue because of, and then you just detect what's the eigenvalue, and then the changing the eigenvalue is because of the error occurred inside the physical qubits, and then you keep that information in the next computations. So that's how the error correction is processing along the protocol. So basically, we have one qubit state. That's so there's 5 qubit physical qubit. 5 physical qubit can only encode one qubit. So basically, you can either put the X logical gate or Z logical qubit, Z logical gates, and so on. But if you want multiple qubit, then you can just combine 5 times more. I mean, 5 times n qubits, physical qubits, to encode n logical qubit. But this one has no control qubit nor Hadamard qubit, so it's not a very useful one. But anyway, that's how you make a multiple logical qubits. Just combining those physical qubits. All right, so I'll introduce more example of the error correction code next time, and then about the surface code maybe next week. So let me know if you have any